July 27th, 1944. The hedgerows of Normandy. Staff Sergeant Curtis Culin of the 102nd Cavalry Reconnaissance Squadron crouched beside his Sherman tank in a makeshift bivouac 3 miles south of Saint-Lô. Around him, the sounds of distant artillery rolled across the bocage like summer thunder. But Culin wasn't thinking about the guns. He was staring at a pile of German beach obstacles, twisted steel beams and angle iron that had been bulldozed off Omaha Beach 6 weeks earlier and dumped here as scrap metal. His crew had been in France for 49 days. In that time, Culin had watched 3 Shermans from his unit burn after hitting German anti-tank mines or taking direct fire from hidden Panzerfausts. The problem wasn't always the enemy's guns. It was the terrain itself. The Norman hedgerows, ancient earthen walls topped with dense vegetation, channeled American armor into predictable routes where German infantry could lie in wait with handheld anti-tank weapons. Every hedge gap became a kill zone, every sunken lane a potential grave. Culin had an idea that his superiors would likely consider somewhere between insubordinate and insane. He wanted to weld steel teeth onto the front of his Sherman, crude cutting blades fashioned from those beach obstacles that would let the tank crash straight through the hedgerows instead of climbing over them or searching for gaps. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The official designation for Culin's tank was the M4A1, a medium tank weighing 30 tons and armed with a 75mm main gun. Its frontal armor measured 51mm on the hull and 76mm on the turret front, against German 88mm anti-tank guns, against Panzerfausts fired at close range, against the long 75mm gun mounted on the Panther tank. This armor was marginal at best. American tank doctrine emphasized mobility and mechanical reliability over armor protection. The theory, developed before anyone understood what combat in the Norman bocage would demand, held that American tanks would maneuver rapidly, use speed and numbers to overwhelm defensive positions, and rely on tank destroyers to handle enemy armor. Reality in the hedgerows had revealed the doctrine's fatal flaws. Shermans couldn't maneuver when every field was a separate fortress enclosed by earthen walls, 12 feet thick and 15 feet high. Speed meant nothing when the only routes forward were narrow lanes pre-registered by German mortars. The Sherman's thin armor, acceptable in theory when tanks would be moving and presenting oblique angles to enemy fire, became a death sentence when tanks had to pause at hedge gaps, exposing their frontal profile while attempting to climb over or push through vegetation so dense it could stop a truck. German infantry learned to position themselves in the hedgerows with Panzerfausts, waiting for American tanks to expose their vulnerable belly armor while climbing the earthen walls. The hollow charge warhead of a Panzerfaust could penetrate up to 200mm of armor. Against a Sherman's belly plate, typically only 25mm thick, the Panzerfaust was devastatingly effective. American casualties among tank crews during the first 6 weeks in Normandy ran far higher than pre-invasion planning had anticipated. In some armoured battalions, crew turnover exceeded 50%. Destroyed or disabled Shermans littered the Norman countryside, testimony to the gap between peacetime planning and combat reality. Tank crews developed their own informal modifications, attempting to improve survivability through field-expedient methods that often violated regulations. Some crews stacked sandbags on the front glacis plate, hoping the extra mass would detonate shaped charges prematurely or provide additional protection against small arms fire. The practice spread rapidly, despite engineering studies showing that wet sand added dangerous weight without meaningfully improving protection. A Sherman with sandbags on the glacis could bog down in soft ground, and the added frontal weight affected the tank's balance, making it more likely to throw a track during sharp turns. Other crews welded spare track links to the hull front, creating a crude layer of additional steel. Tank tracks were manufactured from manganese steel, deliberately hardened to resist wear during normal operations. This hardness made tracks poor armor material, actually. When struck by armor-piercing rounds, hardened track links tended to shatter, sending fragments into the hull or injuring nearby infantry. Still, crews felt compelled to do something, anything, that might improve their odds of surviving the next engagement. The psychological burden of operating a vehicle you believed was inadequately protected affected crew performance measurably. Tankers who felt vulnerable were less willing to take necessary tactical risks, slower to advance when situations demanded speed, more likely to hesitate at critical moments. This erosion of confidence became a tactical liability that commanders struggled to address. Assurances from higher headquarters that the Sherman was adequately armoured for its role rang hollow to crews who had watched friends burn. The United States Army recognized the morale problem but lacked immediate solutions. Improved tanks were in development, the M26 Pershing with its 90mm gun and thicker armour, but production had barely begun and deployment to Europe was months away. The 76mm armed Sherman, which began reaching units in July 1944, offered improved anti-tank capability, but no additional armour protection. Tank crews would fight the remainder of the Normandy campaign, and beyond, in the same M4 variants they'd landed with, protected by the same armour that German weapons could readily penetrate. Into this environment of improvisation and frustration, Curtis Culin brought his hedge-cutting idea. The concept was elegantly practical. Rather than climbing over hedgerows and exposing vulnerable belly armour, a Sherman equipped with steel tusks could plough directly through the earthen wall and dense root system. The tank would remain level, keeping its thickest armour facing forward, and burst through into the adjacent field with speed and surprise, rather than slowly, predictably climbing. Culin fashioned his prototype from scrap metal, welding angle iron, and steel beams into tusk-like projections that extended forward from the Sherman's lower hull. The device weighed approximately 350 pounds, heavy enough to require the tank's momentum to drive it through packed earth and root systems, but not so heavy as to dangerously overload the front suspension. Initial tests conducted informally in a field behind the American lines proved the concept. Cullin's modified Sherman crashed through a hedgerow that normally would have required 15 minutes to navigate carefully. The steel tusks ripped through the earthen wall and vegetation, the tank emerging into the next field in under 30 seconds. No exposed belly armour, no vulnerable pause, just violent forward momentum that could catch defending Germans completely unprepared. Word of Cullin's hedge cutter spread through the tank battalions faster than official communications ever moved. Crews began fabricating their own versions, scavenging steel from destroyed German defences, knocked-out vehicles, and any source of heavy metal that could be shaped and welded. Maintenance sections, officially responsible for keeping vehicles running according to specifications, looked the other way or actively assisted in manufacturing hedge cutters. The devices violated regulations, technically. Attaching unauthorized modifications to military vehicles without engineering approval and testing was grounds for disciplinary action. But no officer was willing to punish tankers for trying to survive. By early August 1944, hundreds of Shermans carried field-fabricated hedge cutters. The devices transformed tactics in the bocage, allowing American armour to advance cross-country instead of being channeled into predictable routes. German defensive tactics, carefully planned around the assumption that American tanks would be constrained by the terrain, suddenly confronted Shermans bursting through hedgerows from unexpected directions. The psychological impact on defending troops was significant. Positions that had seemed secure, protected by dense vegetation and earthen walls, could be overrun by tanks that simply ignored the obstacles. But Culin's hedge cutter, practical and effective as it proved, was purely offensive in application. It helped Shermans attack more effectively through difficult terrain. It did not address the fundamental vulnerability that haunted tank crews every time they climbed into their vehicles. The armour was still too thin. The question of how to meaningfully improve protection remained unanswered. That question would find answers not in official engineering studies or factory modifications, but in hundreds of scattered field, expedient experiments conducted by tankers who understood their vehicles' vulnerabilities intimately and were willing to try anything that might keep them alive. The summer of 1944 became a proving ground for improvised armour solutions that would eventually force the United States Army to confront uncomfortable truths about its primary tank design. The M4 Sherman's armor layout reflected design decisions made in 1941 when the tank was developed. The frontal hull armor, the glacis plate, was 51 millimeters thick and sloped at 56 degrees from vertical. This slope provided effective thickness of approximately 85 millimeters against projectiles striking perpendicular to the surface. Against the German 75mm quick 40 gun mounted on the Panzer IV, this protection was marginally adequate at combat ranges beyond 500 meters. Against the long 75mm quick 42 gun on the Panther tank, the Sherman's glacis could be penetrated reliably at ranges exceeding 1,500 meters. Against the 88mm guns mounted on Tiger tanks or used as towed anti-tank weapons, Sherman armor provided essentially no protection at any combat range. The numbers were unforgiving. A Panther could destroy a Sherman from distances where the Sherman's 75mm gun could not penetrate the Panther's frontal armor in return. The side armor presented even grimmer statistics. The Sherman's hull sides were 38mm thick, vertical with no slope to improve effective thickness. This was sufficient to defeat small arms fire and shell fragments, but utterly inadequate against dedicated anti-tank weapons. A Panzerfaust fired from 50 meters could punch through side armor with ease. The shaped charge warhead created a jet of superheated metal that burned through steel like a cutting torch, igniting ammunition and fuel inside the fighting compartment. American tankers understood these vulnerabilities through experience written in casualty lists and destroyed vehicles. They knew that a Sherman hit in the frontal arc by a German tank's main gun would likely brew up, the grim slang for catastrophic fire that killed or severely burned most of the crew. They knew that German infantry with handheld anti-tank weapons represented a lethal threat at close range, particularly in terrain like the Norman hedgerows, where combat distances shrank to meters rather than hundreds of meters. The official response to these concerns emphasized tactics and training. Tank crews were instructed to avoid frontal engagements with Panthers and Tigers, to maneuver for flank shots where German armor was vulnerable, to coordinate with infantry who could suppress anti-tank weapons. This was sound tactical doctrine in theory, but often impossible to execute in practice. The bocage terrain didn't allow flanking maneuvers when every field was enclosed by impassable hedgerows. Infantry couldn't always suppress hidden Panzerfaust teams before they fired. Some battles simply came down to whether your armor could withstand the enemy's weapons, and in that equation, Sherman crews knew they were at a severe disadvantage. The industrial logic behind the Sherman's armor was clear when examined from the perspective of American manufacturing priorities. The United States was building tanks in enormous numbers, producing more M4 variants than Germany built of all tank types combined during the war. This mass production required standardized designs that could be manufactured in multiple factories using components from hundreds of suppliers. Adding thicker armor meant heavier tanks that required more powerful engines, stronger transmissions, reinforced suspensions, all of which complicated manufacturing and slowed production. American industrial planners made a calculated decision to prioritize quantity over individual vehicle protection, betting that overwhelming numbers and superior logistics would compensate for technical disadvantages in armor thickness. The bet proved correct strategically. American and Allied forces won the war, and Sherman production numbers played a crucial role in that victory. But for individual tank crews, strategic calculations offered cold comfort when a German anti-tank round was burning through their frontal armor. The disconnect between strategic success and tactical vulnerability created the conditions for field-expedient armor modifications that would eventually spread across American armored forces. Tank crews started adding supplemental armor, not because they doubted American industrial capacity or strategic planning, but because they needed to survive the next engagement, tomorrow's advance, in next week's battle. The improvised armor movement began not with a coordinated plan or official sanction, but through scattered individual initiatives by crews desperate to improve their odds. The modifications varied wildly in design, materials, and effectiveness. Some crews continued welding spare track links despite engineering objections. Others scavenged steel plates from destroyed German vehicles, cutting armor from knocked-out Panthers and welding it to Sherman hulls. A few enterprising maintenance sections fabricated custom armor kits using steel delivered for other purposes, commandeering materials through creative requisitioning that didn't appear on official paperwork. The most common approach involved welding additional steel plates directly to the Sherman's frontal hull. Crews would acquire steel plate, usually between 10 and 25 millimeters thick, cut it to fit the glacis, and weld it in place using whatever welding equipment the maintenance section possessed. The added plates were positioned with standoff, a small gap between the supplemental armor and the original hull, created by welding spacer blocks to the hull first, and then attaching the outer plate. This standoff served a critical purpose related to how shaped charge warheads functioned. The Panzerfausts and similar weapons used hollow charge technology, which focused explosive energy into a narrow jet that could penetrate thick armor. The jet formed most effectively at a specific standoff distance from the target. If the jet formed too close or too far from the armor it was attempting to penetrate, effectiveness decreased significantly. Adding an outer plate with several inches of air gap meant that a Panzerfaust warhead would detonate against the outer plate, forming its penetrating jet, which would then have to cross the air gap before striking the main hull armor. The air gap dissipated much of the jet's energy, and the jet itself often became unstable, crossing empty space, degrading its penetrating capability. Theoretical calculations suggested that even relatively thin supplemental armor with proper standoff could provide meaningful protection against shaped charge weapons. Combat testing would prove whether theory matched reality. Not all improvised armor focused on defeating shaped charges. Some crews were more concerned about protection from armor-piercing rounds fired by German tank guns. For this threat, the solution was simpler but heavier. Additional steel plates welded directly to the hull, increasing total thickness and hoping that the extra millimeters would make the difference between penetration and deflection. This approach had obvious limitations. Adding significant weight to the frontal hull affected the Sherman's already marginal power-to-weight ratio. The tank's Ford GAA engine produced 450 horsepower, adequate for the Sherman's 30-ton base weight, but struggling when additional armor pushed combat weight toward 32 or 33 tons. Acceleration decreased, top speed fell, and the transmission, already somewhat fragile in Sherman variants, faced increased stress. Commanders worried that field-modified tanks would break down more frequently, become less mobile tactically, and create maintenance burdens that frontline units couldn't support. These concerns had merit but failed to override crew determination to add protection. Tankers reasoned that a slower tank that survived combat was preferable to a faster tank that burned. If the extra weight caused mechanical problems, maintenance sections would deal with them. The priority was getting through the next battle alive. The welding quality of field-applied armor varied dramatically depending on who performed the work and what equipment was available. Professional welders in maintenance battalions could produce solid welds that properly bonded supplemental plates to hull armor. These welds, when done correctly using appropriate techniques and materials, could actually strengthen the hull structure at the weld points, creating a composite armor system more resistant than either plate alone. Poor quality welds, created by soldiers with minimal training using inadequate equipment, represented potential failure points. A supplemental plate attached with weak welds could break free when the tank moved cross-country, becoming a projectile hazard to nearby infantry. Worse, bad welds could crack under stress, allowing the supplemental plate to shift or vibrate, which actually degraded protection compared to no supplemental armor at all. The Army's Ordnance Department viewed field armor modifications with deep suspicion bordering on alarm. Engineers who had designed the Sherman tank had carefully calculated weight distributions, stress loadings, and performance parameters. Unauthorized modifications threatened to unbalance these calculations in ways that could lead to mechanical failures, tactical vulnerabilities, or crew injuries. Official guidance issued in July and August 1944 discouraged crews from adding supplemental armor without proper engineering review and approval. The guidance was largely ignored. By September 1944, as American armored divisions pushed out of Normandy toward the German border, a significant percentage of Sherman tanks carried some form of field-expedient armor. Estimates based on photographic evidence and unit records suggest that between 15 and 30% of Shermans in frontline combat units had been modified, with the percentage varying by unit and the availability of materials and welding equipment. Some battalions actively encouraged armor modifications, with commanders authorizing maintenance sections to fabricate standardized armor kits that could be applied to multiple vehicles. Other units prohibited modifications entirely, enforcing regulations strictly and punishing crews who violated equipment standards. This inconsistency created bizarre situations where identically equipped tank battalions in adjacent sectors had completely different policies regarding supplemental armor. The debate reached a crisis point in September 1944 when Major General Ernest Harmon, commanding the 2nd Armored Division, officially requested that the Ordnance Department provide standardized armor kits for Sherman tanks. Harmon's request was blunt and supported by detailed casualty analysis from his division's operations in France. His tanks were being destroyed by German anti-tank weapons at rates that threatened operational effectiveness. Crews were improvising armor protection because official supply channels provided no alternative. The Army needed to either provide proper supplemental armor or explicitly prohibit modifications and accept the resulting casualties. The Ordnance Department's response was bureaucratic and technically detailed, arguing that supplemental armor would degrade mobility unacceptably, that field-applied plates could not be properly integrated with the Sherman's existing armor scheme, and that resources would be better spent accelerating production of improved tank designs rather than modifying obsolete ones. The response satisfied no one. Tank crews continued welding steel to their vehicles. Commanders continued requesting official armor kits, and ordnance engineers continued insisting that field modifications were unsound. The impasse was broken by combat results rather than bureaucratic decisions. In late September 1944, near the German border, several Sherman tanks equipped with field-fabricated supplemental armor survived hits from Panzerfausts that would normally have been catastrophic. After-action reports documented that the improvised standoff armor had detonated shaped charges prematurely, dissipating the penetrating jets before they could breach the main hull. Crew casualties in these incidents were 0. Similar hits on unmodified Shermans typically killed or wounded 3 to 4 crew members and destroyed the vehicle. The evidence was impossible to dismiss. Field-expedient armor, despite its crude construction and lack of engineering approval, was saving lives. The Ordnance Department faced an uncomfortable choice: continue opposing modifications and implicitly accept higher casualties, or embrace field armor and work to standardize and improve what crews were already doing anyway. Military necessity and political pressure from field commanders forced the decision. In October 1944, the Ordnance Department authorized development of standardized supplemental armor kits for the M4 Sherman. The authorization came with stipulations designed to preserve some engineering control over what had become a chaotic free-for-all of unauthorized modifications. The armor kits would be designed by professional engineers, manufactured in proper facilities, and installed according to detailed instructions. Weight would be minimized to limit mobility impacts. Quality would be assured through inspection and testing. Crews would no longer need to scavenge materials and improvise mounting schemes, but the authorization came too late to prevent the phenomenon it was intended to control. By the time official armor kits began reaching frontline units in late 1944, thousands of Shermans had already been modified in the field. The improvised armor had become standardized through informal channels, with successful designs being copied from unit to unit and improved through iterative combat testing. The official kits, when they finally arrived, were often inferior to what experienced maintenance crews had already developed. The development of effective supplemental armor required understanding not just what materials to use, but how those materials interacted with German anti-tank weapons under combat conditions. The physics of armor penetration had evolved dramatically during World War II, driven by the arms race between increasingly thick armor and increasingly powerful weapons designed to defeat it. Two fundamentally different weapon types threatened Sherman tanks in 1944. Kinetic energy penetrators, armor-piercing rounds fired from tank guns and anti-tank cannons, relied on velocity and mass to punch through steel. These solid-shot projectiles transferred enormous kinetic energy to a small impact point, shattering or deforming armor until it failed. Against kinetic penetrators, protection came from thickness, hardness, and slope angle that could deflect incoming rounds. Chemical energy weapons, primarily shaped charges like those used in Panzerfausts and Panzerschreck launchers, functioned through entirely different principles. The hollow, charge warhead contained explosive, formed into a cone shape with a metal liner. When detonated, the explosive collapsed the liner inward, forming a jet of superheated metal particles traveling at velocities exceeding 8,000 meters per second. This jet could burn through armor far thicker than the warhead itself, making shaped charges devastatingly effective against tanks. The critical factor for shaped charge effectiveness was standoff distance, the gap between the warhead and the target armor. The penetrating jet formed at a specific distance from the detonation point and then began to dissipate. If the warhead detonated too close to the armor, the jet wouldn't fully form. If it detonated too far away, the jet would break apart before striking. Optimal standoff for most German-shaped charge weapons was between 6 and 8 times the diameter of the cone. For a Panzerfaust with a 100mm diameter warhead, optimal standoff was approximately 600 to 800mm. This physical reality created the theoretical basis for spaced armor. A thin outer plate positioned several inches from the main hull armor could detonate a shaped charge warhead at incorrect standoff distance, causing the penetrating jet to form either too early or in a dispersed pattern. Even if the jet penetrated the outer plate, crossing the air gap would destabilize it, reducing penetrating power against the main armor. The concept was sound in physics laboratories, but combat testing would determine whether field-fabricated versions could achieve meaningful protection. Technical Sergeant Robert Early of the 3rd Armored Division became one of the most prolific designers of improvised armor systems during the autumn of 1944. Early had worked as a welder in a Pittsburgh steel mill before the war, giving him practical knowledge of metallurgy and fabrication that most tankers lacked. His maintenance section, operating behind the division's advance through Belgium in September and October, became an informal research and development facility for supplemental armor. Early's approach was methodical and based on testing rather than guesswork. He acquired damaged Sherman hulls from knocked-out tanks, set them up as targets, and systematically tested different armor configurations using captured German Panzerfausts. The experiments were dangerous, conducted at ranges where warhead detonations could injure personnel, but the data was invaluable. Early discovered that standoff distance mattered enormously, with protection increasing dramatically when the air gap exceeded 4 inches. He found that the thickness of the outer plate was less critical than its structural integrity. A 10mm plate that remained rigid under impact provided better protection than a 20mm plate that flexed or deformed when struck. He learned that weld placement affected performance, with welds around the perimeter of the plate, performing better than welds scattered across the plate's surface. These discoveries, recorded in informal notes and shared through word of mouth, spread through American armored units and influenced how crews fabricated their own armor. The materials used for supplemental armor came from diverse sources, each with advantages and limitations that crews learned to navigate through experience and sometimes painful trial and error. Steel plate intended for construction or structural use, when available through official or unofficial channels, provided consistent quality and predictable properties that made it the preferred material for most installations. This material, typically mild steel with carbon content around 0.2%, could be cut, shaped, and welded using standard equipment available in most maintenance sections. The thickness available varied considerably. Construction steel came in standard dimensions, with 12mm, 16mm, and 20mm, plates being most common in military supplies. Thicker plates provided better protection but increased weight geometrically, A 20mm plate covering the frontal glacis added approximately 400 pounds to the tank's combat weight. Crews had to balance protection against mobility, accepting that every millimetre of added steel meant slower acceleration and increased strain on the transmission and final drives. The cutting and shaping of structural steel presented its own challenges. Maintenance sections used oxyacetylene torches to cut plates to size, working from templates made of cardboard or thin sheet metal. The cuts had to be precise enough to fit the Sherman's curved and angled surfaces, while leaving gaps for welds. Poor cuts meant plates that didn't sit flush against spacer blocks, creating weak points where shaped charge jets could find paths through gaps. Experienced crews learned to cut plates slightly oversized, then grind them to final dimensions, ensuring tight fits that maximized protective value. Armor plate scavenged from destroyed German vehicles offered superior protection per unit weight, as it was specifically designed for ballistic resistance rather than structural applications. Cutting armor from knocked-out Panthers became common practice among maintenance crews, with entire sections dedicated to salvaging usable steel from battlefield wreckage. The side armor of a Panther tank, 40mm thick and manufactured from face-hardened steel, provided excellent protection when repurposed for Sherman supplemental armor. The process of harvesting German armor was labor-intensive and sometimes dangerous. Knocked-out Panthers often contained unexploded ammunition, fuel residue that created fire hazards, and structural damage that made cutting operations precarious. Crews would first thoroughly inspect the wreck, removing any remaining ammunition and draining fuel tanks. Then, using cutting torches, they would remove sections of side armor, typically cutting plates roughly 1 meter square that could be transported back to maintenance areas for final sizing and installation. This salvaged German armor was harder than structural steel, more resistant to penetration by both kinetic and chemical energy weapons. But that hardness created significant challenges for field welding. Hardened armor steel, when heated by welding torches and then allowed to cool rapidly, became brittle and prone to cracking. The metallurgical transformation that occurred during improper welding could actually weaken the armor, creating stress points that might fail catastrophically under combat conditions. Welding hardened armor properly required preheating the steel to temperatures between 300 and 500 degrees Fahrenheit before beginning weld operations. This kept the steel above its critical transformation temperature throughout the welding process, preventing the formation of brittle microstructures. Maintaining preheat in field conditions, often working outdoors in cold weather without proper heating equipment, tested the ingenuity of maintenance personnel. Some crews improvised preheat solutions using multiple torches to warm the work area, or by building fires beneath the tank to heat armor sections before welding. Others used specialized welding rods designed for hard-facing applications, which deposited softer, more ductile weld metal that could accommodate the stress of joining hard armor without cracking. The learning curve was steep, with early attempts often resulting in cracked welds that failed during the first rough cross-country movement. The quality difference between properly welded German armor and poorly welded installations was dramatic. Correctly installed salvaged Panther armor provided protection approaching that of much thicker structural steel, as the face-hardened properties remained effective even after cutting and rewelding. Improperly installed armor, weakened by thermal damage and stress cracking, could actually be more vulnerable than no supplemental armor at all, as fragments from failed welds became projectile hazards inside the tank when struck by enemy fire. Some crews used armor from destroyed German fortifications, cutting steel from pillboxes, bunkers, and the Atlantic Wall fortifications that had been overrun during the Normandy invasion. This material varied wildly in quality, from excellent naval armor plate diverted to fortification construction to mediocre construction steel barely suitable for protective purposes. The inconsistency meant that seemingly identical armor installations could provide dramatically different protection depending on the source material's metallurgical properties and heat treatment history. Identifying the quality of scavenged fortification steel often required destructive testing that crews couldn't perform in field conditions. Some maintenance sections developed rule-of-thumb methods for assessing steel hardness striking samples with hammers and judging hardness by the depth of the impact mark and the quality of the rebound. These crude tests provided rough guidance but couldn't replace proper metallurgical analysis, leading to situations where crews welded armor that looked substantial but provided minimal protective benefit. Concrete cutting operations to extract steel from reinforced German fortifications required specialized equipment and considerable time. Diamond-tipped cutting wheels or pneumatic breakers were needed to separate steel reinforcing bars or embedded armor plates from surrounding concrete. The effort was worthwhile only for particularly high-quality armor, such as naval plate used in coastal defense positions, where the steel's superior properties justified hours of extraction work. Track links remained popular despite their questionable effectiveness against kinetic penetrators and the engineering studies demonstrating their limitations. The advantage of track links was immediate availability. Every tank carried spare track sections, and ease of installation. They could be bolted or wired to existing armor or welded in place without complex fabrication. The psychological benefit of track link armor exceeded its actual protective value in many cases, giving crews the sense that they had improved their protection even when the improvement was marginal. Against shaped charges, track links provided some degradation of the penetrating jet through multiple impact surfaces and air gaps between individual links. A Panzerfaust warhead striking track links would detonate against the outer surface of the first link, forming its penetrating jet. That jet would then have to burn through the remaining thickness of the first link, cross the air gap to the next link, and penetrate subsequent layers before reaching the main hull armor. Each transition degraded the jet's coherence and energy, potentially reducing its penetrating power enough to prevent hull penetration. Against armor-piercing rounds fired from tank guns, track-link armor performed unpredictably and often dangerously. The hardened track steel, designed to resist wear from contact with road surfaces and track pins, was extremely hard but also brittle. When struck by a kinetic penetrator traveling at high velocity, track links tended to shatter rather than deform plastically. The shattering created a spray of steel fragments that could injure nearby infantry or, in some documented cases, penetrate the thin armor of the tank's side skirts or engine deck. Some armor-piercing rounds striking track links deflected at unusual angles due to the irregular surface presented by the overlapping links. These deflections occasionally sent rounds tumbling away from the tank, providing protection through sheer randomness rather than engineered effectiveness. But the unpredictability meant crews couldn't rely on track-link armor, and engineers were correct to caution against its use as a primary protective measure. The most sophisticated field armor systems, developed through iterative combat testing and refinement, combined multiple approaches in integrated designs that addressed both shaped charge and kinetic penetrator threats. A typical advanced installation might include a 20mm mild steel plate mounted 4 to 6 inches in front of the glasses using spacer blocks welded to the hull. The spacer blocks, typically fabricated from steel angle, iron or channel, created the standoff distance critical for defeating shaped charges. On top of this base plate, crews would weld sections of track link to add additional disruption for shaped charge jets. The track links were positioned to overlap slightly, creating multiple layers of steel with air gaps between each link. Against a Panzerfaust, this arrangement forced the penetrating jet to burn through the outer track links, cross the air gap to the base plate, penetrate the base plate, cross the 6-inch standoff gap, and finally attempt to penetrate the Sherman's main glacis armor. Few shaped charge weapons of 1944 vintage retained sufficient energy to complete this sequence successfully. Additional protection came from welding steel brackets at the sides of supplemental armor plates, creating small vertical surfaces that could deflect or destabilize kinetic penetrators, striking at oblique angles. These brackets, typically 50 to 75 millimeters tall and fabricated from angle iron, added minimal weight but created additional opportunities for enemy rounds to deflect or tumble before striking main armor. The concept borrowed from German Sherman side skirts, which had demonstrated effectiveness at defeating certain types of projectiles through similar mechanisms. The total added weight of a fully implemented advanced armor system could reach 800 to 1,000 pounds, concentrated on the frontal arc. This weight significantly impacted the Sherman acceleration and maximum speed, reducing top speed by approximately 2 to 3 miles per hour and noticeably degrading acceleration from a standstill. The front suspension, designed for the tank's base weight of 30 tons, operated under increased stress that accelerated wear on springs, shock absorbers, and wheel bearings. Maintenance officers tracked mechanical reliability statistics for armor-modified tanks compared to standard configurations, attempting to quantify the cost of supplemental protection in terms of increased maintenance requirements and reduced operational availability. The data showed measurable increases in track throwing incidents, where the added frontal weight caused track misalignment that led to tracks separating from road wheels during sharp turns. Front road wheel bearing failures increased by approximately 15% in heavily armored tanks. Some crews used armor from destroyed German fortifications, cutting steel from pillboxes, bunkers, and Atlantic Wall fortifications that had been overrun during the Normandy invasion. This material varied wildly in quality, from excellent naval armor plate to mediocre construction steel, requiring crews to test samples before committing to fabrication. The inconsistency meant that seemingly identical armor installations could provide dramatically different protection depending on the source material's properties. Track links remained popular despite their questionable effectiveness against kinetic penetrators. The advantage of track links was availability. Every tank carried spare track sections, and ease of installation. They could be bolted or welded in place without complex fabrication. Against shaped charges, track links provided some degradation of the penetrating jet through multiple impact surfaces and air gaps between individual links. Against armor-piercing rounds, hardened track steel tended to shatter rather than deform, occasionally deflecting projectiles through sheer unpredictability, but often fragmenting in ways that endangered nearby personnel. The most sophisticated field armor systems combined multiple approaches. A typical advanced installation might include a 20mm mild steel plate mounted 4 to 6 inches in front of the glacis, using spacer blocks welded to the hull, with sections of track link welded to the outer plate to add additional disruption for shaped charge jets. The total added weight could reach 800 to 1,000 pounds on the frontal arc alone, significantly impacting acceleration and mobility, but providing meaningful protection against the weapons most likely to kill crews. Installation quality varied as much as design sophistication. Professional maintenance battalions could fabricate and install armor systems that looked nearly factory-produced, with precise cuts, clean welds, and proper structural integration. These installations distributed weight appropriately, avoided interfering with driver, vision, or bow machine gun operation, and could be removed if necessary without damaging the underlying hull. Field installations by tank crews using improvised equipment ranged from adequate to dangerously poor. Some welds were so weak they failed during normal cross-country movement, causing supplemental plates to fall off or shift into positions that blocked driver vision or jammed turret traverse. Other installations were welded so extensively and heavily that removing them would require cutting torches and extensive repair work, effectively making the modifications permanent whether or not they proved beneficial. The Army's growing acceptance of field armor led to efforts to standardize and improve the practice. In November 1944, Ordnance technical bulletins began circulating with guidelines for supplemental armor installation. The bulletins acknowledged the reality that crews were adding armor, regardless of official policy, and attempted to channel that energy into methods less likely to cause mechanical problems or injuries. Recommended designs, specified standoff distances, suggested materials based on availability, and provided welding procedures appropriate for field conditions. Weight limits were established to prevent overloading the front suspension excessively. Installation instructions emphasized maintaining driver visibility and ensuring that added armor didn't interfere with escape hatches, a grim reminder that even protected tanks could be destroyed and crews needed rapid exit routes. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The most comprehensive test of field-expedient armour came not in controlled experiments, but in the brutal combat of the Battle of the Bulge. Germany's massive surprise offensive launched in the Ardennes region of Belgium on December 16, 1944. The offensive caught American forces unprepared, with 3 German armies totaling over 400,000 men and more than 600 tanks and assault guns achieving complete tactical surprise. German panzer divisions penetrated deep into Allied lines, creating a bulge in the front lines that gave the battle its name and threatening to reach the Meuse River and beyond. American armoured units rushed to contain the breakthrough, often engaging German armour in conditions that heavily favoured the defender. The Ardennes terrain, characterized by dense forests, steep hillsides, and narrow valleys, channeled tank movement into predictable routes along roads and valley floors. German forces, having planned the offensive meticulously, positioned anti-tank weapons at choke points where American reinforcements would be forced to advance in column formation, vulnerable to ambush. The weather during the Bulge eliminated one of America's greatest advantages. Heavy cloud cover, fog, and snow grounded Allied tactical aircraft for most of the battle's first week, removing the air support that usually compensated for American tanks' technical disadvantages against German armour. P-47 Thunderbolts and P-51 Mustangs, which had achieved near total air superiority over European battlefields by late 1944, sat uselessly on airfields while German tanks advanced under protective cloud cover. German forces fought with determination born of desperation, knowing this offensive represented their last chance to influence the war's outcome before American and Soviet forces closed on Germany from both directions. Tank engagements occurred at close range in forested terrain where American crews couldn't employ their preferred tactics of maneuver and standoff engagement. German Panther tanks, operating from defensive positions or moving through familiar terrain, engaged American Shermans at ranges where the Panthers' superior gun and armour provided overwhelming advantages. The 2nd Armoured Division, Hell on Wheels, heavily engaged near the northern shoulder of the German penetration around the town of Grande-Ménil, fielded significant numbers of Shermans with field-applied supplemental armour. The division had spent months in relatively static positions before the offensive, allowing maintenance sections extended time to fabricate and install armour systems. Photographic evidence from December 1944 shows that approximately 60% of the division's Shermans carried visible supplemental armour, ranging from simple track-link installations to complex multi-layer systems. Combat reports from December 1944 through January 1945 documented multiple incidents where modified Shermans survived hits that would normally have been fatal. On December 22nd, during fighting near Grande-Ménil, a Sherman from the 66th Armoured Regiment, commanded by Sergeant James Morrison, took a Panzerfaust hit on its supplemental glacis armour, at a range of approximately 40 metres. German infantry had infiltrated close to American positions during the night, positioning themselves in buildings overlooking the road where Morrison's tank platoon was advancing. The Panzerfaust, fired from a second-story window, struck Morrison's Sherman almost perpendicular to the frontal armour. The shaped charge warhead detonated against the outer steel plate, a 20mm mild steel section mounted 5 inches in front of the glacis. The explosion was visible to Morrison's crew as a bright flash and a shower of sparks, accompanied by a tremendous bang that resonated through the hull. Morrison's driver, believing they had been fatally hit, began to evacuate the tank according to training drilled into every crew. But Morrison, watching from the turret, saw no smoke or fire. The penetrating jet had burned through the supplemental plate but dissipated, crossing the air gap behind it. The jet struck the main glacis armour with insufficient energy to penetrate, scorching the paint and deforming the steel slightly, but failing to breach the hull. The impact left a distinctive mark on the glacis, a star-shaped pattern of heat damage approximately 4 inches in diameter, surrounded by areas where paint had blistered from thermal effects. Morrison's crew, shaken but uninjured, reversed their tank to cover behind a stone building and continued fighting. They located the German infantry position that had fired the Panzerfaust and destroyed it with high-explosive rounds and machine gun fire. Without the supplemental armour, post-battle analysis determined, The hit would likely have penetrated the main armour, the typical penetration pattern for a Panzerfaust hitting Sherman glacis armour at perpendicular angles, igniting ammunition stored in the hull, and likely killing the driver and bow gunner instantly. Similar survivals occurred repeatedly during the bulge, fighting across the entire front. On December 23rd, a Sherman from the 3rd Armoured Division's 32nd Armoured Regiment absorbed 3 separate Panzerschreck hits during close-range fighting in the village of Houghton. All 3 hits struck supplemental armour, 2 on the frontal glacis and 1 on a field-fabricated side plate that the crew had installed to protect against infantry anti-tank weapons. None of the hits penetrated to the main hull. The crew fought their tank for 4 more hours before withdrawing due to mechanical problems unrelated to the enemy hits. On Christmas Day, during the defence of Bastogne, a Sherman from the 4th Armoured Division, moving to relieve the encircled garrison, took a hit from a German PaK-40 anti-tank gun firing armour-piercing rounds. The round struck the Sherman's supplemental armour at an oblique angle, approximately 30 degrees from perpendicular. The projectile, a 75mm armour-piercing capped round travelling at roughly 700 meters per second, struck the outer plate and deflected upward, tumbling over the turret without penetrating either the supplemental armour or the main hull. The deflection resulted partly from the supplemental plate's positioning and partly from luck, as armour-piercing rounds striking at angles can behave unpredictably. But the crew credited their survival to the supplemental armour, reasoning that without it the round would have struck the main glacis at an angle more favourable for penetration. Whether this assessment was technically correct mattered less than its effect on crew morale, which remained high despite the desperate tactical situation. Shermans with field armour absorbed hits from Panzerfausts, Panzerschrecks, and even some glancing blows from tank guns that might otherwise have penetrated. The added protection didn't make Shermans invulnerable, and many armour-modified tanks were still destroyed during the fighting. But the protection measurably improved crew survival rates in units that had widely adopted armour modifications compared to units fighting with standard tanks, a difference that became apparent when casualty reports were compiled after the battle. Statistical analysis performed by Army Ordnance researchers in February 1945, examining casualty data from the bulge, revealed stark differences in survivability between armour-modified and standard Shermans. Tank battalions, where more than 50% of Shermans carried supplemental armour, experienced crew casualty rates approximately 30% lower than battalions with predominantly unmodified tanks, when controlling for similar combat intensity, enemy opposition, and terrain factors. The analysis was not without limitations. Battalions that had time and resources to modify their tanks extensively were often the same units that had been in theatre longest, with experienced crews and well-developed tactical procedures. Separating the protective benefit of armour from the survival advantage of experience proved statistically challenging. Additionally, armour-modified tanks tended to be concentrated in certain units based on the initiatives of individual commanders or the capabilities of particular maintenance sections, creating sample distribution problems that complicated statistical confidence. Despite these limitations, the trend was clear enough to convince skeptics within the Ordnance Department that field armour provided real benefits worth supporting. The data showed that hits which would typically result in catastrophic kills, burning vehicles with total crew loss, instead resulted in damaged but repairable vehicles with crews that survived when supplemental armour successfully defeated the attacking weapon. Even accounting for possible confounding factors, the evidence suggested that armour modifications were saving lives at rates that justified their cost in weight and mobility. Not all supplemental armour proved effective. Some installations, poorly designed or inadequately constructed, failed catastrophically when tested by combat. Thin outer plates without proper standoff provided no meaningful protection and added weight that degraded mobility for no benefit. Plates welded too close to the main hull detonated shaped charges at nearly optimal standoff distance, actually increasing penetration in some cases compared to bare armour. Weak welds allowed plates to shift or detach, creating hazards for accompanying infantry who could be struck by falling steel. The worst cases involved armor that interfered with tank operations. Several incidents were reported of supplemental armor blocking driver vision, contributing to accidents where Shermans collided with obstacles or other vehicles. At least one case documented armor installation that prevented proper turret traverse, leaving the tank unable to engage targets outside a restricted arc. These failures reinforced the importance of proper design and installation, validating the Ordnance Department's concerns about uncontrolled modifications. German responses to American supplemental armor evolved as the war progressed. Intelligence reports reaching German tank commanders by late 1944 noted that many American Shermans now carried additional frontal armor. German crews were instructed to aim for areas not protected by supplemental plates, particularly the lower hull below the level where most added armor was positioned, or the turret, which rarely carried field modifications due to weight and balance concerns. German anti-tank teams adapted their tactics, attempting when possible to engage Shermans from the side where supplemental armor was less common, or from elevated positions where they could fire down into thinner top armor. These tactical adjustments reduced, but did not eliminate, the protective benefit of field armor. The adaptation-counter-adaptation cycle that characterized all aspects of armored warfare continued, with both sides seeking advantages within the constraints imposed by their equipment and resources. The arrival of factory-produced armor kits in late 1944 and early 1945 created an awkward situation for units that had already modified their tanks extensively. The official kits, designated as supplemental armor sets and shipped with detailed installation instructions, represented the Ordnance Department's attempt to standardize protection that crews had been improvising for months. But the official kits often provided less protection than the best field-fabricated systems, being designed with conservative weight limits and manufacturing constraints that limited effectiveness. Many units ignored the official kits entirely, preferring armor systems they had developed through combat testing and iterative improvement. This rejection of official solutions in favor of field-expedient alternatives frustrated ordnance planners, but reflected combat veterans' pragmatic assessment of what worked. Crews trusted armor they had seen stop German weapons more than armor designed by engineers who had never been shot at. Other units used official kits as starting points, adding field modifications to supplement the factory armor. A Sherman might receive the official armor set, then have additional plates welded on by the maintenance section, or have track links added to the factory armor for extra disruption of shaped charge jets. These hybrid systems combined official engineering with field experience, often achieving better results than either approach alone. The fundamental tension between official engineering and field improvisation never fully resolved during the war. Engineers had legitimate concerns about modifications that affected vehicle performance, reliability, and safety in ways that crew members might not fully appreciate. Field soldiers had equally legitimate frustrations with equipment that didn't adequately protect them, and bureaucratic processes too slow to address urgent combat needs. The compromise was messy and inconsistent, but it reflected the reality that modern warfare was too complex and fast-moving for centralized control of every equipment modification. The experiences with Sherman supplemental armor influenced post-war American tank development profoundly. When the Army began designing the M46 Patton tank in the late 1940s, armor protection received far higher priority than it had in the Sherman's design. The Patton featured significantly thicker frontal armor, over 100 mm on the glacis, reflecting lessons about the importance of protection that Sherman crews had learned at terrible cost. The M60 series tanks that followed incorporated composite armor concepts influenced directly by field-expedient spaced armor from World War II. The M60's armor included integral spacing in critical areas, applying in factory production the same principles that Sherman crews had improvised, with welded plates and air gaps. Soviet tank designs evolved similarly, with spaced armor becoming standard in designs from the 1950s onward. Modern main battle tanks like the Monet Abrams use composite armor that takes spacing concepts to sophisticated levels, with multiple layers of different materials separated by gaps that disrupt both kinetic and chemical energy penetrators. The Abrams frontal armor incorporates depleted uranium mesh, ceramic plates, and steel in a complex arrangement designed to defeat modern anti-tank weapons that are far more powerful than World War II Panzerfausts. But the underlying principle, using spacing and multiple layers to disrupt penetrators, traces directly back to improvised Sherman armor from 1944. The psychological dimensions of supplemental armor extended beyond simple crew confidence. Knowing that their tank had been modified, even if the modifications were crude and of uncertain effectiveness, gave crews a sense of agency and control that official equipment alone could not provide. They had taken action to improve their own survival, rather than passively accepting whatever protection the army issued. This sense of active participation in their own defense had measurable effects on morale and combat effectiveness. Tank crews that modified their own armor, or worked with maintenance sections to install improvements, developed deeper understanding of their vehicles' vulnerabilities and the weapons they faced. The process of fabricating and installing armor required thinking carefully about where German weapons were most likely to hit, what angles of attack were most dangerous, and how different armor configurations might perform under various combat conditions. This education made crews more tactically aware and better able to position their tanks to maximize whatever protection they possessed. The modifications also created visible differences between tanks, allowing crews to personalize their vehicles in small ways, within the generally uniform structure of military equipment. A Sherman with a particular armor configuration became identified with its crew, distinguished from other Shermans in the company by the specific pattern of supplemental plates or track links. This personalization, minor as it might seem, contributed to crew cohesion and the sense that they were fighting in their tank, a vehicle they had shaped and improved, rather than an anonymous piece of equipment. German tank crews, though generally operating technically superior Panthers and Tigers, observed the American armor modifications with professional respect. German after-action reports occasionally noted that American tanks were becoming more difficult to destroy, requiring more carefully aimed shots or repeated hits. Some German commanders expressed frustration that the Americans were improving their tanks' protection while German tanks fought with standard armor, unable to field-modify their vehicles due to lack of materials, welding equipment, and time for such work. The contrast reflected broader differences in how the two sides approached equipment and doctrine. American forces, backed by overwhelming industrial capacity and logistical support, could afford to experiment and improvise, treating individual vehicles as expendable resources that could be modified, damaged, and replaced. German forces, operating with shrinking resources and under constant air attack, needed every tank to perform exactly as designed, with no room for field experimentation that might compromise already limited combat power. The final months of the war in Europe saw supplemental armor reach maximum proliferation. By March 1945, photographic evidence suggests that over half of Shermans in frontline American armored divisions carried some form of field-applied or factory-issued supplemental protection. The modifications had become so common that unmodified tanks were noteworthy exceptions rather than the standard configuration. Crews replacing losses or receiving new tanks from depots routinely added armor as soon as practical, often before the tank entered combat. The effectiveness of this armor in the war's final phase was difficult to assess separately from the general collapse of German resistance. By April 1945, German tank strength had declined catastrophically due to fuel shortages, lack of replacement vehicles, and the destruction of experienced crews. American tanks faced less opposition from German armor and more from hastily prepared infantry defensive positions. In this environment, supplemental armor continued, providing protection against handheld anti-tank weapons, but the intense tank versus tank combat that had characterized earlier fighting became increasingly rare. Victory in Europe, achieved on May 8, 1945, ended the immediate need for Sherman supplemental armor. The Pacific Theater, where American forces faced Japanese opposition that included some tanks but relied more heavily on fortified positions and infantry anti-tank tactics, saw different patterns of armor modification. Pacific Shermans often carried extra armor on the sides and rear rather than frontal arc, protecting against infantry attacks from hidden positions in jungle terrain. The specific modifications varied by theater and tactical situation, but the underlying principle, that crews would adapt their equipment to meet the threats they actually faced, remained constant. The post-war fate of armor-modified Shermans varied. Tanks returned to the United States for storage or disposal generally had supplemental armor removed during depot-level maintenance, returning the vehicles to standard configuration. Shermans transferred to Allied nations often retained their modifications, particularly when the recipient nation lacked capacity to perform major rework. Israeli Shermans, fighting in 1948 and subsequently, carried armor. Modifications descended directly from American World War II patterns, adapted for local materials and threats. Curtis Culin, whose hedge cutter innovation had sparked the broader wave of field modifications, received the Legion of Merit for his contribution to armored warfare. The award citation specifically noted that his device had saved numerous American lives by allowing tanks to avoid predictable routes where German anti-tank teams waited. Culin returned to civilian life after the war and worked as an engineer, rarely speaking publicly about his wartime innovation. He died in 1963, his obituary mentioning only briefly his service in the armored cavalry. Robert Early, whose systematic testing had refined supplemental armor designs, remained in the army after the war and eventually retired as a sergeant major. His informal notes on armor testing, preserved in unit files, were later reviewed by Army Ordnance researchers studying armor protection. Some of Early's observations about standoff distances and shaped charge defeat mechanisms appeared uncredited in post-war technical publications about spaced armor design. The thousands of tankers who welded steel to their Shermans, who scavenged materials from battlefields, who spent precious rest time improving their tanks' protection, mostly returned to anonymous civilian lives. No medals were awarded for field armor fabrication. No official recognition acknowledged the initiative and ingenuity that crews demonstrated in addressing their equipment's shortcomings. The Army's official histories mentioned supplemental armor only briefly, generally in the context of unauthorized modifications that complicated logistics and maintenance. Yet the legacy of those modifications extends far beyond individual recognition. Every modern tank design incorporates lessons about armor protection that were first learned by Sherman crews, discovering what worked and what didn't, through combat testing measured in lives. The principle that soldiers facing danger will adapt their equipment, regardless of regulations or official policy, has shaped military procurement and doctrine for decades. The recognition that user experience and frontline feedback must inform equipment development, not just laboratory testing and engineering theory, became embedded in post-war military culture. The M4 Sherman tank, judged by technical specifications alone, was inferior to German heavy tanks in armor protection and firepower. But war is not fought by specifications. It is fought by human beings using whatever resources they possess to accomplish missions and survive. Sherman crews demonstrated that inferior equipment, intelligently modified and skillfully employed, could compete effectively against superior designs. The supplemental armor they fabricated from scrap steel and determination represented the application of practical engineering to urgent problems, solving issues that official channels had failed to address. The question of whether Sherman tanks needed supplemental armor or whether they were adequately protected by design remains debated among military historians. Casualty statistics show that Sherman crew survival rates, while lower than ideal, were not catastrophically worse than crews in other nations' tanks when accounting for combat intensity and tactical employment. The Sherman's thin armor was a conscious design choice, trading protection for mobility, mechanical reliability, and production efficiency. That choice proved strategically sound, as American armored forces won the campaigns they fought. But statistics and strategic assessments offer little comfort to individual soldiers who must close with the enemy in vehicles they know can be penetrated by enemy weapons. The tank crews who welded supplemental armor to their Shermans were not making strategic calculations. They were responding to the immediate reality that German weapons could kill them, and any protection that might improve their odds was worth the effort to install. Whether their fears were statistically justified or whether supplemental armor was objectively necessary misses the fundamental point that soldiers confronting danger will take protective measures when possible, and military organizations must either support those efforts or futilely attempt to suppress them. The Sherman supplemental armor phenomenon stands as testimony to soldier initiative and the gap between equipment as designed and equipment as needed. It demonstrates the limits of centralized planning when confronting the chaos and unpredictability of combat. Most importantly, it honors the pragmatic ingenuity of the men who refused to accept vulnerability as inevitable and worked within their means to improve their chances of survival and mission success. The crude welded plates, the scavenged armor sections, the track links bolted to hull fronts, all represented acts of defiance against both enemy weapons and institutional inertia. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.